quiz review today, okay, for tomorrow. So let me start off by making sure that you have the resources that, or you know where to find these resources. First is, let me make sure here. Okay, first is that I have derivative and integral rules available on my website under today's link. I think this is helpful to print out just so that you can have all the rules in front of you as you're deciding what rules to match, especially with use substitution. But I'll also attach this to the back of your quiz, so either in person or remote through Teams. I'll have this so that you'll have access to it. And second is I also have this integration technique checklist that I've kind of gone through a lot of these guidelines in class, and I feel like maybe it's good for me to just list it all on, organize it into a summary sheet, so that maybe that'll provide some support and allow for you to have very structured way of going through and looking through problems or identifying the appropriate method. So I'm going to just use this just to kind of highlight and kind of recap what our process is going to be as we work through these problems in preparation for tomorrow's quiz. So every problem we should try to see if power rule is an option, right? And the quick way to tell is look in the denominator. If your denominator is separated by plus or minus, with terms separated by plus or minus, you know that rearranging and power rule is probably not going to be an option. Okay, but if you look at these examples here, example 1, notice that you have parentheses all over the place. You have square root in the you have square root in the expression, but neither of these are use substitution problems. We can expand without running into any issue that's preventing us from rearranging. So I want to make sure that we can look at a problem and decide whether expansion is possible or whether we need to scrap that first option and consider our second option of use substitution. Now, if there are more than one term in the denominator, or even if we see families of functions that prevents us from being able to merge terms, like exponential function or trig function or natural log function, we know we gotta go to our second option. So our second option is use substitution. Most of our problems are going to fall under this category, but we just want to make sure that we don't forget about just doing a quick check for expansion power rule. And the reason why is because if you go down the use substitution path when it's not a use substitution problem, a lot of students get stuck, and it's a lot harder for students to go back and backtrack and consider expansion when they've already gone halfway down use substitution and trying to figure out, where they went wrong. They feel like they did something wrong in the process, and they're already knee deep in use substitution steps. It's hard to go back and consider a different method. So sometimes though, with use substitution, it's kind of hard to pick out that U value. So my suggestion is, start easy, right? Can you find a set of parentheses? If you can, then let that be your first guess as to your U value. But outside of that, I have a list of these guidelines that you can read over as to where the U value is located. But ultimately, you know that you're just trying to move your way towards a known integral rule, right? So whatever it takes to get to that U value, where it will match with one of the integral rules, right? That's the path that we want to take.
Pardon the interruption. Ms. Sandra Barber, please report to 5308. Ms. Sandra Barber, please report to 5308.
So sometimes it's kind of tough for me to say your U value is always located here or it's always located there, because it can be a number of different places. But the one constant that we can count on is that if you go through your substitution, you're trying to make it match one of these rules, right? After the dust settles, you should be able to get it matched exactly with one of these. Now, these are just the main ones here, like power rule, 1 over u, e to the u. You know, there are other trigs involved, which you can find on the formula sheet. But you know, these are the ones that are the most common ones. So whatever it takes to get to one of these rules is whatever you want your u value to be. Sometimes it's just an exponent, sometimes it is in the denominator, sometimes it's the full denominator, sometimes it's just a portion of the denominator. But two things are going to happen. All your x's will cancel out, and second, once you get past the coefficient, it'll look exactly like one of these rules, right? If you cannot make your problem look exactly like one of these rules, then either you went down the wrong, either it's a use substitution problem, but you just went through the wrong steps, or maybe it's not a use substitution problem and we just completely went down the wrong path. But I think that's just why the more practice we get, the more comfortable we're going to be able to pick out our u value. Now, sometimes your u substitution doesn't quite get you there, where you have like an x left over, or just something small left over. And if that's the case, we can potentially consider another set of u substitution. This is the change of variable, where we're like one variable away from getting all the x's in terms of u. So we can rearrange our expression that's assigned to u and solve for x and make that second set of substitution. And then finally, if it doesn't fall under either power rule or u substitution, we have a third option, and that is synthetic division or long division. And the way that you can tell whether it's a potential long division or synthetic division is it has to be a rational expression. Okay, we can't have any natural log, any trig, any exponential functions, but something where it looks like a, like a polynomial over another polynomial, right? But there are some restrictions here. Your numerator degree has to be at least the same degree, if not higher, than the denominator. So if the denominator degree is higher than numerator, then there's no chance that long division, synthetic division can work. But I noticed that I can't do power rule because there's too many terms in the denominator, but both these terms, both these expressions, my numerator is at least the same, if not higher, than the denominator degree. And the way they can tell the difference between whether it's a long division or synthetic division is you look at the degree. If it's anything higher than the first degree, you got to do long division. If it is a first degree, you can do synthetic, but anything with synthetic you can also do with long division. So you have some options there. All right, so just a summary over the process that we're going to be working through with all these problems: power rule, u substitution, and long division in that order. Okay, that's the checklist. So let's look at number 1. This is off the quiz review, number 1. So dx over 2x plus 3. Okay, now if you'd like, you can push that dx out if it feels more familiar. but they're the same thing. All right, can I rearrange this and rely on maybe power rule expansion? What do you think? Yeah. Denominator, we instantly can tell not an option, right? As soon as you see a plus or minus in the denominator, you know that that first option is out. So our next option is use substitution. What could be our u value? Yeah, that denominator, right? That denominator looks like it's going to be, if we let that u value be that denominator, we can quickly work towards a rule that we can identify. Okay. So several guidelines that are on this checklist is, right, denominator is a good place to look for your u value, especially if you don't see a set of parentheses. But it does come with some exceptions. Natural log and square root of x, sometimes those are the appropriate u values, and sometimes they are located in the numerator. All right, we make our initial round of substitution here. Pull the 1/2 out in front. And once you're there, right, perfect match, right? Cover up that coefficient up, perfect match. And then bring our x variable back into our answer. Okay, any questions with one? All right, number 2, expansion, rearrange. Okay, very similar to number 1, right? We can't do anything with that denominator with so many terms. So use substitution. What's our u value?
4x squared plus 1.
Yeah, very similar to number 1, right? The only difference is that the degree is a little different, and we have that x left over, but we should be able to get a nice match. That x squared through a derivative should be able to handle that x. So very similar to number 1. So see if you can practice those steps like number 1 and work your way down, and let's compare our answers after you guys work through number 2. All right, so in your answer, what did you get as your coefficient in front?
1/8.
1/8, okay. All right, let's check our answer. Check our work. Okay, any questions with 2? Let's look at number 3. All right, what do you notice about number 3?
The numerator has 2 terms, the denominator has 1.
Okay, so can we explore option number 1? The numerator has multiple terms.
Oh, yeah.
Okay, so the numerator is not the issue, right? The denominator, we're okay, right? That x, we can, now it doesn't mean that after cleaning up that it's all going to be power rule, but at least we can explore that cleanup process, right? That x is movable with, and we're able to make progress in terms of cleanup that was not possible with problem at number 2. So I want to just make sure that we see that distinction here. So, but what we can do is we know that we can avoid use substitution. Okay, so that's the big thing I want to make sure that we see. We can avoid use substitution. If you go through use substitution, you're going to run into a dead end. Okay, so this is not a use substitution problem. Now, we know we can resolve that x in the denominator. There's only one variable below, but I want to just make sure that we know how to clean this up. You can choose between 2 different ways of rearranging this, but as long as you can pick one way that you're comfortable with, that's what I'm more concerned about. I don't care which way you choose. But the first way that I taught you guys, or that I showed you guys, was to bring that x up to the top. But I do know that this method, sometimes students run into an issue. Either they don't change the sign of the exponent, or they forget to put another set of parentheses, right? There's no set of parentheses here, but once you bring that x up, we need to make sure that that denominator gets seen by every term in the numerator. So from here, we can distribute, right? Another way is to ensure that you're going to make every term see the denominator, is think in terms of adding and subtracting fractions, right? If you add and subtract fractions, they all have common denominator. So here we have the merging of terms that all have the common denominator of x. So you can just split them back up into individual fractions. And I guess maybe the advantage of this method is it kind of forces you to remember that every term is impacted by the denominator. But either way, we're going to get to the same point of our problem. I can clean this up to be just 2 minus 5 over x. In this same place, I can distribute this through. This is x to the first power. Add exponents, 1 minus 1 is 0. And then 5x to the negative 1 dx, right? These mean the same thing. So let me ask you then, once you're here, these are 2 separate terms, which is nice because we can handle each with their own unique rule. What rule can we handle with integral of 2?
X.
Yeah, so just power rule, right? How about 5 over x?
Could also be power rule.
Okay. What's the issue with power rule with this setting?
When you add the exponent, x is 0.
Yeah, so remember we talked about how, yes, I think it's good that we're always thinking power rule because that is, that's the umbrella of all these problems, right? We should always explore power rule, especially in this form. But after we see this enough, we're going to see that this is the exception to the rule, right? We have a special rule where power rule can't handle, and that is the what? Yeah, that's the x to the negative 1, which is natural log rule, right? That's the exception. So yes, we have power rule, and then we have a natural log rule. Now, maybe to help you see a little better, I can rewrite this as 2 separate problems, and I can push that 5 out in front to make it even easier to spot the pattern. But now we can just apply the appropriate rule, right? There's no need for use substitution. There's power rule here. And I guess you can do use substitution, but really it's just, you're just changing one variable, which you can just jump directly to the answer without having to go through that. All right, any questions with 3? All right, anybody still need to look at 3? All right, let's look at number 4 here. Can we move things around? Too many terms denominator, right? We're kind of stuck. If it was x plus 1 over x, we could, but not x over x plus 1. So we're stuck in this form. Our next option is use substitution. Is there a u value that we can pick out? So you know what? There's actually multiple ways that we can work through this problem, but let's go down that use substitution path. What could be a u value that we can maybe start with? The x plus 1. But we do know that there's going to be some hurdle that that's going to come up ahead, right? What issue are we going to foresee with this process? Okay, that x is not going to go away on its own, but it's a minor. That's not a minor thing, but it's not too difficult for us to make that adjustment, right? Now, if the numerator was like, x cubed minus 4x plus 3, we just know that there's 2. But if it's only just x or just an x squared, we know that we can just do that additional use substitution, change a variable to kind of handle that, patch up that one little issue. But yeah, this is one method that we can go through where use substitution and just a little bit more at the end to take care of that x. All right, let's see where this takes us initially. So we can't move forward until that x is somehow resolved. And how can we do that?
Solve for u.
Yeah, we take our expression assigned to u, we rearrange it. X equals u minus 1. And then this is now going to replace that x. And now we're in a better position to move forward here. Now there's only one term in the denominator. Now we can split up. So I can think of it as u over u minus 1 over u. Which is fine. If you want, you can make it more visual, make it into 2 separate integral problems, and then you can just see that both will be applied separately. What does 1 turn into? Now look at
Oh, u.
Yeah, this is a little bit strange, right? I mean, normally we don't do this in terms of u, but in this case, this is all kind of under the umbrella of u variable, so we do need to turn that into a u because it's not x, right? Yeah, so that's something that we haven't quite seen yet. So this is going to turn into u. And what about 1 over u?
Ln u.
Yeah, so we have u minus natural log absolute value of u plus c. U is only a temporary variable. We still got to bring back what? Okay, x plus 1. Now, let me talk about something that we haven't talked about explicitly here. If you leave your answer like this, it's fine. I'm not going to take any points off, but I do want to point something out here. Is there a way to get this to be a little bit cleaner than what this is showing? Give you a hint. Something about that plus 1.
Oh, it goes away since you have plus.
Yeah, so you can actually take that +1 and make it get absorbed in that plus c, right? So c represents all the constants. So if there's any leftover constant, we can just kind of push it all into that category. So, I mean, I'm not taking any points off, but I just want to show this to you because if you come across this problem on the AP exam and you're looking and this is what you got, and the only answer choice is this, that's why. It's because they're taking any constant and they're just making it merge into that plus c. So, but I mean, I'm not taking any points off. This isn't wrong. It's just this is how a multiple choice question would represent their answer. Okay. Now, this is one method, which is perfectly fine. We can actually do something completely different with this problem. Anybody see another option that's possible with this problem?
I was about to say synthetic division, but no.
We can do synthetic, yeah, or long division actually. So we do have multiple terms in the denominator. It is kind of like a rational expression. Your numerator degree is the same, if not greater than the denominator. Okay, so this is one of those problems where it kind of falls into two separate categories. Now, if it was a quiz or a test, you can choose which method. I'm not going to say you got to work, a problem every method possible. But I do want to show you the different methods, and in case you prefer one method over the other, you have the option to choose. So this is 4 from a synthetic division perspective. And I'll show it using long division as well. We do have that denominator being x plus 1. We know we can do synthetic because that x is to the first power. So I'm going to have to choose the factor that I'm going to be using, which is going to be always the opposite sign of what you see there. So you're going to take -1, put it outside like a little half rectangular box. And we're going to list out the degrees that we see in the numerator. So, list out the coefficients. So what number can we put here? What's in front of the x?
1.
1. Okay, so we're going to put a 1 here. Now, I want to backtrack with what I said before. Before I said that we need to put a 0 for any degree that's skipped over, right? If you see x cubed followed by x, we need that 0 there, which is still true. But what I said before was not to put anything after your term. So if it was missing a constant, just leave it alone. Don't need to put a 0 there. But I'm going to backtrack and say that I think it's good to work your way all the way down to that constant, because even if you don't use it, at least it's there to help you remind you that there is a column for that constant. So we have a column for the linear, but let's also have a 0 as a placeholder for that constant. Okay, we may not use it, but it's always good. I think in this case, we're actually going to see it being beneficial. All right, so synthetic division process, we're going to always bring the first number below the line. Multiply with the divisor, or with the adjusted divisor here. We get -1. Add. Okay, and then we stop, right? The constant is going to be the last column that we're going to be worried about. So it's very short. This starts off with x. After synthetic division, this is going to drop down to what? Remember, with synthetic division, every degree is going to drop by 1. So this is just going to be a constant, right? So if this is a constant, then this must be the remainder. So very short synthetic division process. Again, this doesn't solve the problem, but it will present an easier path towards identifying a rule. So this will result in the same thing that we got above. 1 will turn into x, and then the 1 over x plus 1 is just going to be a natural log use substitution problem, natural log of x plus 1 plus c. You can go through U substitution if you like, but I think we can save some steps, right? That's a U value. There's no coefficient. I can just make that go into my U value and finish it off. Same result, different process. Now, anything with synthetic division, you can also do using long division. So let me show that as well. So long division, we're going to take our divisor, put it outside, our long division notation. And we're always going to look to match the first terms of each expression. X times what gives us X? Just 1. And this is helpful. Put the parentheses around the divisor as a reminder that you're distributing the top to all the terms. So 1 times X is X. 1 times 1 is 1. Draw your line, change your signs. Your first term will always match and pair up to be 0. Bring down the -1. Can we go any further? Yeah, this is too low, right? So we call this the remainder. And we write our remainder as divided by our divisor. Same result as synthetic division. And same answer. So this is one of those unusual problems where it falls into two completely different categories: U substitution, change of variable, and long division and synthetic division. So I don't know if there's a clear-cut method that is easier than all the others, but at least you have options to choose. Okay, questions with 4. Number 5. Can we expand this? So there is only one term in the denominator, right? So I'm going to kind of say that there's some exceptions, right? I say that when there's one term in the denominator, you can bring it up and merge with the others, but the natural log kind of throws a wrench into that, right? It's a different family of function. We know that the x and natural log isn't just going to merge into something that we can apply power rule with. Right? We can't even do power rule with natural log. So just want to point out that, yes, there's only one term in the denominator, but that natural log. Now, if it was x plus 1 squared, then we could expand and we can go along that path. But that natural log already eliminates the possibility of it being just power rule problem. So our next option down is use substitution, right? We don't have a rule that matches exactly like that one. So that's got to be use substitution because doesn't match any of these restrictive rules that we have. So what's our u value?
ln x.
Okay, why?
Because the derivative of ln x is just is 1 over x.
Okay, so you're thinking ahead and you're matching. You're already thinking in terms of matching, which is great. But visually, what's easy about this u value? Say it again. Or what's easy about identifying this u value? That's what I want to say. Okay, I already said a parentheses. Okay. Now, if you're looking ahead and you're thinking how things are going to work, how things are going to match up, I think that's great. But I find that this is easier in terms of, if you can't look that far, at least you should be able to see the set of parentheses and be able to pick out that u value. Again, it's not 100% accurate, but that's a quick way to start that process, right? If you can't see down the path, at least you can pick out the u value because the parentheses is already there for you. And if the parentheses isn't there, then think about, is there a way for me to rewrite the problem so that I get a set of parentheses? Now, if I can't get a parentheses anywhere, then I gotta consider, okay, maybe I need to consider the denominator. Maybe I need to look to kind of keep back and forth between my problem and the rules that are available, and then see a match, and then find the u value. Those are the harder ones. I find that these are a little easier because the parentheses is already there for you, ready for you to make that next step. Okay. All right, so derivative 1 over x. And just like what Oscar was saying, just looking ahead, knowing that this x is going to take care of itself down the road. And I talked about how numerator is usually not a good place for the u value, but natural log is kind of strange, right? It produces a derivative in the denominator, and it's going to handle that x nicely. Okay, cross multiply. All right, let's see where this leads. Just like what we suspected, x goes away. Nice, clean expression in terms of u, and we can apply what for this? Just power rule, right? That's just the first rule that we learned for u substitution, power rule. Don't forget, bring your original variable back into the problem. I like to push coefficient down in front, but you can leave it in the denominator. It's up to you. As long as you understand these are the same things. Number 6. Can I move, rearrange?
Can you distribute the root x?
I could, but first things first, though, can I move everything up to the numerator? Am I going to be able to rely on just power rule? All right, I just want to make sure that we can eliminate that option, right? That plus is already going to eliminate the option. Okay, so we know that our first option is out. Our second option is use substitution. And Oscar, you asked, can we distribute that root x? We could, but what's helpful about this problem, though, the way it is?
It has a parentheses.
It already has parentheses. So I think if you see a set of parentheses, let that be something that helps you, right? If you distribute the root x through, I think in some problems you do want to distribute, especially if this is all in the numerator, then that's what I would do. If this is in the numerator, I would distribute because I know that I'm just going to clean this up and rely on power rule. But if I see a denominator and I know that expansion is not going to be possible, then the parentheses is there to help you. It's there to help you identify that u value. Okay. So I feel like everything that I'm saying down the road, I'm changing it a little bit and saying, well, except in this case, right? This is one of those things where, right, this is fine to expand in the numerator, but denominator, we kind of have to reconsider. All right, how can we get this ready for derivative here?
X to the 1.
Yeah. One goes away. Before I cross multiply, I typically like to clean up my negative exponent. Just feels a little cleaner. And then even when I'm cross multiplying, I keep looking back at my problem and I say, well, maybe just a little bit even cleaner if I can just get that back to a square root, just to visually it just matches up nicer, but you don't have to. Just trying to always look at what visually will be a cleaner match. All right, so replace what I underlined here. So du over root x, the root x stays. I'm sorry, I put a du here. I pushed that dx out. But you can leave it in the numerator. But if I want to do that, I got to put a 1 here. But you can replace dx and have it just 2 root x over du over root x du. Sorry, root xu. Either way, we see that we have a nice match with the x's getting resolved. We push the 2 out in front. And what rule do we use here? Natural log, okay. Now I want to point out a potential pitfall because we see this so often now that we kind of are blind to, we can be blind to just thinking that it's always going to be natural log. So I just want to make sure that I want to put something that's slightly different but very similar, and I want to ask you, can we still use natural log here? What if instead of 1 over u, it was 1 over u to the 1/2? Can I still use natural log and just adjust it and say, well, that 1/2, I can just put it up here? This is completely different, right? How do we handle this problem?
Would be a power rule?
Yeah, it's a power rule. So I don't want us to think that just because you see a u in the denominator, that's automatically going to be natural log. U to the first power is natural log. Everything else is power rule. This is actually the exception to the rule. Okay? The rule is mainly power rule. So here we got to bring this up. So let me work this out so you can see it and see that distinction here. Completely different category here. Push that 1/2 as 4, 2. 2 times 2 is 4. So look at how different the answer looks. Just because that slight adjustment there completely changes the rule that we use, even though they look virtually identical. Right? Let's go to number 10. Okay, everybody good? So when I see this problem, I know that this doesn't match any of my rules. It's just too much going on, right? There's an exponential, there's secant tangent. I already know that I can't just match a rule and use it. So, and expansion is out of the picture as well. It's not even the same family of functions here. So it's got to be U substitution. But it's hard to know where the U value is, right? It could be anywhere. There's no parentheses that's obvious. So I think this is one of those problems where we may have to look at our possible integral rules and decide what is going to be the best fit that we can work towards? What's a possible end goal that we can have in mind? If you can have an end goal in mind, then you can kind of go back and compare the setup and decide a lot easier what the u-value is. I think this is one of those problems where you kind of want to scan your possible integral rules and decide which is the one that you want to use, and then backtrack and then decide on the u-value. So what rule does this look like we could fit under?
A to
Okay, it's going to be this a to the u. Okay, now this 5 is an exponential function. It's not base e. We call this base a because it's a base that's other than e. If it's other than e, they're all different, but they all kind of have a similar pattern. So we call it base a. So a could be base 2, could be base 5, could be base 8, right? So we need to recognize that this is an exponential function that is base 5, and it falls under this a to the u category. So if you can see that this is the end goal, then it's a lot easier from here on out, right? What's the u-value then? Secant x, right? So if you can look at this as your end goal, then it's a lot easier to see, okay, well, it's got to be the exponent if I want to make this work out. Okay. All right, so let's start there. Now, secant is a derivative from first semester. And if you look on your formula sheet, secant x is going to be secant tangent. That's the derivative. Okay, but it's on that big formula sheet. Cross multiply. We make our substitutions. Cleans up nicely, no coefficient. And now we just follow what the rule says. And then bring back your x variable. Okay, I want to squeeze in one more problem. This is number 13, but I changed it a little bit. Now, the nice thing about this problem is you look at this and you're saying, well, the tangent and secant are clearly separated, so I can just look at the rules. They're not divided by one another. I can treat them like separate rules, and I can just find my match. So we don't have to necessarily look at an overall u-value that will fit into this. We can treat them like two separate problems. So that's nice. Next thing is, well, let's see, what rule is going to match up with tangent of 2x and secant of x? And if we look on our summary, on our formula sheet, matches nicely with one of these new rules that we learned here. So tangent matches nicely here. Secant matches nicely here. So I think we jump directly in, right? This is going to be pretty straightforward. But this, we got to do a little bit of what? Not rearranging, just we have something that sticks out more than just x, right? Yeah, so we got to go through a little bit of u substitution, okay, just a little bit. But essentially, the rules are already there. We just have to kind of put things in place. So this requires a little bit of u substitution. But this, we can jump directly into the rule, because anytime you can replace x with just u, you can just jump into the rule. There's no need to, there's not going to be any changes that we got to adjust. So. So I'm gonna just put an integral here as well, just to indicate. All right, I'm just gonna do two separate process here. One, I gotta do a little bit more work with. I get integral of tangent of u times du over 2. Push that 1/2 out. And that tangent u is simply just going to be negative natural log cosine u. And I'm just going to go ahead and bring that 2x back in. And then for secant, if you look at the rule, just follow the, -4. The -4 will have to be in front. But then the rule is just natural log secant, secant x plus tangent x. So just following it to the letter here. Okay. One final thing. I want to eventually get to the point where the simple u substitution problems, we can avoid u substitution, not avoid it, but we can just jump to the end without having to go through and rewrite it every time. And for these simple u substitution problems, what pattern do you see? That 2 is going to produce a what? 1/2. So that's always the pattern. So if you know that pattern, you can go from here to the rule and then just push out that coefficient as the fractional value. But I do want to make sure that we are comfortable and that we understand that process, because I think what happens is I see students, they think that it is chain rule from first semester and they just put a 2 out in front. But as long as you understand that we're doing the other direction, then whatever coefficient you have here, you're just going to take the derivative of that and then just take the fractional value, or just flip it. And that, once you're comfortable, you can jump to that step, and that will save you some steps down the road. All right, so help session this afternoon and tomorrow morning. Both will be recorded. Your quiz will be relatively short, just 6 questions, right? But I encourage you, work through. I have another review worksheets under today's link, so get the practice that you need. But I'm available to help this afternoon and tomorrow morning. All right, thanks everyone. Hope you guys have a great day. See you tomorrow.